Good morning. We are going today to see series circuits with Ohm's law. So first of all, what's a series circuit? Well, a circuit in series is a circuit where the electrons have only one path to go. No choice, there is no branches to take, there is no node in a circuit, it's one path. Example. Let's have a little battery right here. So the positive terminal again is a long one. That's the negative terminal. And I'm going to have a little resistor right here. We're going to call it R1. I'm going to have another one right here. I'm going to call it R2. And I'm just going to complete the circuit like this. Okay. So as you can see here, the electrons are going to be leaving the positive side of the terminal. Again, it's a conventional directions for electricity. Just leave it at that. They're going to go through the first resistor, then they're going to go through the second resistor and go back to the other terminal of the battery. Okay. So they don't have a choice, they have to go that way. That makes this circuit a series circuit. Okay. Now, whether it's a series circuit, a parallel circuit, or an hybrid circuit, the idea is always the same. What is the current leaving the battery? What is the current going through the first resistor? What is the current going through the second resistor? Because it's in series here, they're all equal to one another. So I can already write that down. And we also need to know the voltage dropped by the first resistor, the voltage dropped by the second resistor. And when you are asked to study a circuit, essentially, these are the questions you're supposed to answer. Okay? So, in order to do this, we need to know the electromotric force. We want to know the voltage essentially supplied by the battery. We want to know also the value of the first resistor, and we want to know the value of the second resistor. Once I know those three things, I can definitely calculate everything else. Okay. So let's make up an example here. Let's pretend that right here we have a 12-volt power supply. Let's pretend that right here R1 is going to be a 330 ohm resistor, and let's pretend that R2 is going to be a 470 ohm resistor. Now, a little note, little aside right here. Why 330 ohm and why 470 ohms? Well, manufacturers don't make all kind of resistances or resistors. Okay. But 330 ohm is a very common value, 470 ohm is a very common value. If I wanted, for example, 300 ohms for a certain application, I could, but not with one resistance only. I would have to associate different resistances or use a potentiometer, which is a mechanically adjustable resistance. Okay, so how do we proceed with this information to answer those questions? Well, when you're in a series circuit, the first thing that you need to do, it's always going to be like this, is that you're going to calculate the equivalent resistance. And the equivalent resistance for series circuit is going to be essentially equal to the sum of all the individual resistances. So in our example here, it's going to be just R1 plus R2, which is going to be 330 plus 470. Therefore, our equivalent resistance, it's going to be 800 ohms. Okay? So that's always what you're supposed to do. Calculate the equivalent resistance. Once you have the equivalent resistance, maybe, and that would be my advice, we can redraw the circuit. So we are going to still have our battery, which is a 12-volt battery, as we know. We are going to have our equivalent resistance, which is a 800 ohm resistance. Okay, so we're going to redraw the circuit, and we're going to calculate I, the current leaving the battery in the configuration of having just a battery and an equivalent resistance. So according to Ohm's law, I is equal to V over R, which in this case means that you're going to have 12 volts over 800 ohms. If it is not clear as to where the 12 volts come from for this voltage drop right here, I would like to invite you to refer to the previous video on Ohm's law's formula and example. Okay, so calculator time. 12 divided by 800 equal 0.015. So we're going to have 0.015 amps, or if I prefer, 15 milliamps. Okay. Now, the interesting thing about this 15 milliamps is that it is the current throughout the circuit, which means that if I go back to the original drawing, this is going to be 15 milliamps right here, and it's going to be 15 milliamps here as well. Okay, so I is equal to I1 is equal to I2, and it's equal to 15 milliamps. If now I want to calculate VR1 and VR2, let's go to the next page. There we go. We know that VR1 is going to be, according to Ohm's law, R1 times I1, and VR2 is going to be equal to R2 times I2. So if you recall, R1 was 330 ohms, I1 is 0.015 amps. In order to have an answer in volts, make sure that you keep ohms and amps and not milliamps. And here you're going to have 470 ohms times 0.015 amps. Okay. So again, calculator times. So we're going to have right here 4.95 volts, and here you're going to have 470 times 0.015. You're going to have 7.05 volts. So far so good? Alright. So we have answered all the questions. We have calculated the current everywhere. It's going to be 15 milliamps through the first resistor, 15 milliamps through the second resistor. The first resistor drops 4.95 volts, and the second resistor drops 7.05 volts. So we have achieved our goal of calculating everything. Before we go further, though, I want to point out something to you. If you remember from the previous video, we talked about KVL, Kirchhoff's voltage law, in which I stated that the sum of the voltage of the sources was equal to the sum of the voltage of the loads. The sources being the battery, in this case we have 12 volts. And here the loads are essentially the voltages consumed by the two resistances. So we have 4.95 volts and 7.05 volts. I just want you to verify that 12 is indeed equal to 4.95 plus 7.05. Some of you might think, well, as soon as I know that the first voltage drop is 4.95, can I subtract that from the 12 volt to find this one? The answer is yes, absolutely, and actually quite a clever shortcut. Okay, I will demonstrate more about those shortcuts in the hybrid calculation video. Okay. All right then, see you next time.